For a given series sum of an, we would like to test this for the convergence using the ratio test. So if the general form of the series is given in the form an, we can find the an plus first term of the series, and what we want is I would like to find the limit of the ratio of the an plus 1 to the an. So when an goes to the infinity in its module, in its absolute value. So the first case is when this limit exists and this limit is equal to some constant L. So if this constant L is less than 1, then the series an is convergent. So if this limit doesn't exist, or if this limit exists, and equal to the L, which is bigger than 1, or this limit does not exist, in this cases, the series an is divergent. Well, there is a third case when this limit is equal to the 1. So in the third case, if this limit of the ratio of the an plus 1 to the an, when an goes to the infinity, is equal to the 1, then in this case the test is inconclusive. It means that we don't know whether this series is convergent or divergent because the test doesn't work basically for this type of the series. So let's consider examples. So one example for the convergent test and one example for the divergent test. Divergent case. Say example. So let's say we're given a series, actual alternating series, minus 1 in the power of n, n in the power of 3, divided to the 3 in the power of n. So basically a couple of first terms of the series can be written in the form. So if I substitute n to be equal to the 1 to here, and here, and here, we're going to get minus 1 multiplied to the 1 in the power of 3 divided to the 3 in the power of 1, right? So 1 over 3 basically. Plus, say minus 1 in the power of 2 is going to be a 1, simply, right? So 2 in the power of 3, it's going to be 8 divided to the 9. Or, so if I substitute the 3, it's going to be minus 1 in the power of 3, which is minus 1 again, right? So 3 in the power of 3 divided to the 3 in the power of 3, which is 1 again. Plus, so if I substitute 4 to here, it's going to be 64 over 81. So we can continue this until the infinity. So what I want is I would like to just know whether this sum is going to be a finite number or it's going to be an infinite number. So in order to do this, I would like to write down the general form of the series. It's going to be minus 1 in the power of n cubed divided to the 3 in the power of n. And an plus 1, it's going to be, so I'm going to just write down n plus 1 in all possible appearances of the n here, right? So for all appearances of the n, I'm just going to write down the n plus 1. It's going to be minus 1 in the power of n plus 1 multiplied to the n plus 1 in a cube divided to the 3 in the power of n plus 1. So what I need to check is, I need to find the limit of n goes to the infinity, an plus 1 divided to the an in its absolute value. So please note that I can write down this limit in the form n goes to the infinity. So since I'm taking the absolute values, I can just neglect the minus 1s in the power of n's. So I would like to write this in the form an plus 1 multiplied to the reciprocal of the an, right? So I would like to write down the an plus 1. So it is going to be this part. So a plus 1 in a cube divided to the 3n plus 1 multiplied to the reciprocal of the an. Reciprocal means I'm going to just write down 1 over an, right? So if I write this down, it is going to be in the form 3 in the power of n divided to the n cube, right? So let me rewrite first of all. 3 in the power of n plus 1 in the form is 3 in the power of n multiplied to the 3 in the power of 1, right? So we know that if we multiply the same number in the different powers, we can just write down this number in the power of this, the sum of the powers, right? So it's multiplied to the 3 in the power of n divided to the n cube, right? So here I can cancel 3 in the power of n and 3 power of n, and what I'm going to have is 1 over 3, which is a constant, and I can take this out from the limits. So it is going to be multiplied to the limit of n plus 1 in a cube. I can open up the brackets, right? Using the formula, it's going to be n cube plus 3n squared plus 3n plus 1 divided to the n cube, right? And this limit is going to be equal to the 1 because I can divide both parts of this ratio, this part and this part of this ratio, separately to the n cube, right? So let me write this. So I can write this 1 over n cube here, and here it's the same 1 over n cube. So I can multiply it as a 1 over n cube, the numerator and denominator separately. So this doesn't change the ratio, right? So in this case, it's going to be 1 plus 3 over n plus 3 over n squared plus 1 over n cube divided to the 1. So when n goes to the infinity, this term, and this term are going to 0. And what is left is simply 1 over 3. So the limit of the ratio of an plus 1 to the an exists, and this is equal to the constant, which is less than 1. So that is why, using the ratio test, we can make the conclusion that the series minus 1, 3 in the power of n cubed divided to the 3 in the power of n, n cubed divided to the 3 in the power of n goes from 1 to the infinity, is absolute convergent. So let's consider the second example. In this example, we're going to test for the convergence of the following series. N in the power of n divided to the n factorials. So basically, I would like to remind you that n factorials, it's a multiplication of the numbers, of the natural numbers, starting from 1. 1 multiplied to the 2, multiplied to the 3, multiplied to the 4, until the n, right? So that is why the couple of first terms of the series can be written in the form. So 1 divided to the 1 plus, if I substitute the 2, it's going to be 2 in the power of 2 divided to the 2 factorials, which is 2, right? Plus 3 in the power of 3 divided to the 3 factorials, which is 6, plus 4 in the power of 4 divided to the 4 factorials, which is 24, plus and so on. So what I want is, I would like to know whether this series is going to converge to some number, right? So the sum of these terms of the series is going to be a finite number or infinite number. So in order to do this, let me first of all write down the general form of the series. It's going to be n in the power of n divided to the n factorials, and the n plus first term is going to be, so when I'm just substituting all the appearances of the n here with the n plus 1, it's going to be n plus 1 in the power of n plus 1 divided to the n plus 1 factorials. So let me rewrite this a slightly different form. So I would like to write as n plus 1 in the power of n multiplied to the n plus 1, first of all, and I would like to rewrite the n plus 1 factorials in the form as 1 multiplied to the 2 multiplied and so on multiplied to the n multiplied to the n plus 1, right? So actually, this part of this term is simply n factorials. So I can write this in the form n plus 1 in the power of n multiplied to the n plus 1 divided to the n factorials multiplied to the n plus 1, right? So the only thing which we need to do is we need to find the limit of an plus 1 multiplied to the reciprocal of the an when n goes to the infinity in its absolute value. So since all the terms here are positive, we can just neglect this module operation. It's going to be n goes to the infinity. An plus 1 can be written as n plus 1 in the power of n multiplied to the n plus 1 divided to the n factorials multiplied to the n plus 1 multiplied to the reciprocal of this en, which is like, I just need to write this, flip the numerator and denominator with the places. It's going to be n factorials divided to the n in the power of n. So here we can cancel this term, this term, this term, and this term, and what is left is the limit of n plus 1 in the power of n divided to the n in the power of n when n goes to infinity. So since both of the terms have the same power, we can just write them with a common power. N plus 1 divided to the n in the power of n, and I can just write this in the following form. 1 plus 1 over n in the power of n when n goes to infinity. So when n goes to infinity, this is the spatial limit, which is going to be equal to the e, right? Basically, it is this definition of the e, right? So do you remember the e is a constant, which is defined roughly as 2.721. So again, the limit of the ratio exists, and this is equal to some number which is bigger than 1. So that is why this series is going to diverge, right? So the series n in the power of n divided to the n factorial when n goes to the from 1 to the infinity is divergent. So let us consider the case where the ratio, the limit of the ratio is equal to the 1. The most obvious example would be just a harmonic series, right? So let us consider the series 1 over n goes from 1 to the infinity. It's a harmonic series. So n's term of the series is going to be 1 over n, and n plus first term of the series is going to be 1 over n plus 1, right? So if we evaluate the limit of an plus 1 divided to the an when n goes to the infinity, it is going to be the limit of 1 over n plus 1 divided to the 1 over n goes to the infinity, it is going to be the limit of n divided to the n plus 1 when n goes to the infinity, which is equal to the 1. So the test doesn't tell us whether the series, the following series, is convergent or divergent. The same is for the limit when n goes from 1 to the infinity for the following series, 1 over n squared, right? So if we find the limit of the ratio of the an plus 1 to the an, so an plus 1 to the an, its limit when n goes to the infinity, it's going to be the limit of n goes to the infinity. This is 1 over n plus 1 in a square divided to the 1 over n square. So this is can be written in the form n squared divided to the n plus 1 in a square, right? N goes to the infinity. So we can open up the brackets in the denominator. It's going to be n squared plus tn plus 1. And in the numerator we have the n, right? So if we divide everything to the n squared, we're going to have again the 1. So actually for all the series in the form n in the power 1 over n in the power of p, when n goes to from 1 to the infinity, the ratio test is inconclusive. So you see in a case when the limit is equal to the 1, the test doesn't work, right? So sometimes, so this series is divergent and the limit is equal to the 1, the ratio limit is equal to the 1, and this series is convergent and the ratio limit is equal to the 1. So that is why we can't say anything about the series if the limit is equal to the 1.